Let's talk about anomeric carbon. So let me show you what is it. So here we have the structure of, let's say, alpha and beta glucose. If you look at the first carbon, this is okay. Let's just see the linear chain structure of glucose first. We have 6 carbons in glucose, and then on the first carbon we have aldehyde functional group because glucose is an aldehydic sugar, right? When you form a ring structure, if you put glucose in aqueous medium, it's going to form a ring. Now it can either be alpha ring or beta ring. What is it? Let's understand that in very simple terms. See, when glucose is going to form a ring, this first carbon is actually going to make a bond with the first carbon. Fifth carbon is going to make a bond with the first carbon. So what happens is there are 6 carbons in glucose, so it makes a hexagon ring. The 6th carbon is always outside of the ring, so we have first, second, third, fourth, and 5th and 6th carbon. 6 carbons in glucose, fine. The first carbon is a special carbon because it had a functional group aldehyde. Now this first carbon is called anomeric carbon because if on the basis of the first carbon we divide glucose as alpha and beta form, what are these forms? These are actually isomers, special type of isomers that are called as anomers, and we talked about them in detail in the class, right? Now what are anomers? And just a quick review. Anomers are a type of isomers if the first, not the first carbon, we are talking about the first carbon, if it have like OH on the downward side, so it's going to be alpha form, and the opposite of it, I mean the first carbon, if it have like a OH group on the upward side, then it's going to be called as the beta form. So these are called anomers, and the first carbon is called as anomeric carbon. Fine. So if you're going to have free anomeric carbons, then it's going to be a reducing sugar. If you have no free anomeric carbon, what is free? I mean, free means that it don't really participate in forming a bond. Okay, for example, maltose is a reducing sugar. So if you look at the structure of maltose, it forms bond. This is alpha glucose, they combine together, they form a disaccharide called as maltose. We already know that. Now when it forms a bond, it's going to be between the first carbon and the 4th carbon, so alpha 1,4 glycosidic bond. This is maltose. So the first carbon, this is anomeric carbon. Here the first carbon is occupied, it's not free, but then you have a free anomeric carbon in maltose. This one is free here, so it's a reducing sugar. Now if you look at the structure of sucrose, it's a non-reducing sugar. How? Let's see. So in sucrose you combine alpha glucose plus beta fructose. So basically beta is a ketonic sugar, so the second carbon is your anomeric carbon. And if you look at the first carbon, now this is aldehydic sugar, the same glucose that we just talked about in maltose. This first carbon makes a bond with the second carbon. So this anomeric carbon and this anomeric carbon, they are making a bond. They both are occupied. There is no anomeric carbon which is free. So it's a non-reducing sugar. So sucrose is a non-reducing sugar. We can also talk about lactose here. So lactose is a disaccharide of beta glucose plus beta galactose. It makes a bond between first carbon here and the 4th carbon. First carbon is anomeric carbon, 4th is not an anomeric carbon, so they both make a bond here. It forms beta 1,4 glycosidic bond. So this anomeric carbon is occupied, but then you have a free anomeric carbon, this one here, so it's a reducing sugar. Got it? Now we know what is anomeric carbon. So let's talk about which statement here is correct about it. So anomeric carbon, they are only present in polysaccharides. That's all right, because we just saw in disaccharides we had anomeric carbon. It is the carbon that becomes chiral upon ring closure. In amino acid, we talk about chiral carbon. A carbon which has 4 different groups is called as a chiral carbon. So as I told you earlier, that when you make a bond, when you make a ring structure from a chain structure, so for example, it's just an example of glucose here, because I have a structure of it right now. So when this 5th carbon is going to join hands with the 1st carbon, so this 1st carbon is your anomeric carbon, and this will help basically in forming the chain. When it will form a chain, it will become, it's actually closing the ring by combining with the 1st carbon. And then second point was that when it will form a ring, it will, this 1st carbon, the anomeric carbon, is actually going to be a chiral carbon because it will have 4 different groups. If you look at the structure of glucose here, where is my anomeric carbon? Where is it? Look at the structure. Which one is my anomeric carbon? Of course, the 1st carbon. Why? Because glucose is aldehydic sugar. Aldehyde functional group is on my 1st carbon. So this 1st carbon is called anomeric carbon, and this decides if the sugar is going to be reducing or non-reducing. This decides if it's going to be alpha or beta form, right? And here the 1st carbon, this is carbon, right? It has hydrogen 1, and then glucose is going to make 4 bonds, right? It has hydrogen and then OH, and it's combined to another carbon here, and then on the 4th bond it has oxygen. So it means that these all 4 things are different from each other, which means its anomeric carbon is for the closure of the ring. It formed a ring structure in glucose or any other sugar, and then it's a chiral carbon, which means that it has 4 different groups. So chirality is basically formed or produced when any carbon is going to have 4 different groups. A chiral carbon has the ability to rotate light, which means it's optically active, as we studied about in amino acid, right? So almost every amino acid except for glycine, they are chiral carbons. They are optically active. Okay, so the same applies here. This anomeric carbon is a chiral carbon closing the ring. So the second statement makes sense. And then if you look at all the rest of the statements, like it is always carbon 6 in aldohexoses. So the anomeric carbon is carbon 1 if it's aldehydic sugar. It's carbon 2. The anomeric carbon is carbon 2 for ketonic sugars. Fine. But most of the times, because almost all the sugars that we have, including glucose, galactose, almost all of them are aldehydic sugars. Okay, they are aldohexoses, and that is why most of the times you are going to have 1st carbon as anomeric carbon. But if you look at fructose, then it's going to be 2nd carbon. It's going to be an anomeric carbon for fructose. But anyways, it's not the 6th carbon, definitely not. It's going to be 1st carbon for aldohexoses. Aldohexoses means that hexose sugars which has aldehydic functional group like glucose and galactose. And then it says that anomeric carbon is lost when a glycosidic bond is formed. That's not right, because anomeric carbon is actually responsible for making the glycosidic bond in one of the sugars in a disaccharide. For example, like if it's a maltose, right? So it's alpha sugar glucose plus alpha glucose. So alpha glucose 1st carbon is going to make a bond with the 4th carbon of this alpha glucose. So it's not lost. It don't really go anywhere. It's in the ring. It is actually responsible for making the ring, so it's not lost. That's an incorrect statement. It determines whether a sugar is an aldose or ketone. That's not right, because anomeric carbon, it decides whether a sugar is reducing, non-reducing, or it decides if it's alpha form or beta form of the sugar, while the functional group aldose and ketone, it is not decided or determined by anomeric carbon. Okay, so option B is the correct option here.